the lost time. So just apology for that inconvenience. I shouldn't be doing that, interfering with your study time, but I hope you indulge me. So today we just want to continue where we left. The last discussion was about power. So I'm just going to do a review and then take some questions, and then from there continue, right? So I will share my screen. Go on this mode. I am in class. Please, would you phone after past 11? I want a new page. Share that one. Okay, I hope you can see that page, right? So, let's go for this. I'm going to review power in AC, right? Okay. Now, the basic thing that we have to understand is that in an AC circuit, we are dealing with sinusoidal quantities, which voltage can be defined by this equation, plus phi, and then the current in a circuit can also be defined by this equation, I peak in omega t plus a different angle. So this is the situation that we have. We have a source. It's an AC source. And it's got a load, which is a general impedance, right? A general impedance. So it is driven from a voltage, which is sinusoidal, and the current that is flowing is sinusoidal, right? So the idea is to define the power that this load is going to take from the source. We saw that in terms of sinusoidal quantities, if we use Z as a pure resistor, it led us to define two important things, or should I say one, the peak voltage divided by √2, giving us a new quantity which we call the voltage RMS value, or root mean square value. And the current, in a similar fashion, has got a root mean square value, which is given by I peak over √2. These two quantities here, the root mean square voltage, the root mean square current, are normally what we mention or specify when we talk about AC voltages. So when you hear 220 volts, 400 volts, those voltages are actually root mean square values. But in normal talk or normal application, people don't say 220 root mean square voltage. They'll just say 220 volts. So it's implied that it is a root mean square quantity. Let's say the root mean square quantity is that magnitude of an AC voltage that will give the same power as a DC source of the same magnitude, right? So if you have a peak AC voltage, I'm saying peak, I did not say RMS. So if this is peak, right? The DC voltage that will give the same amount of power in a resistor as this AC voltage with a 220 volt peak will be 220 divided by root 2. So if you applied this AC voltage to a resistor, right, a 20 ohm resistor, that 20 ohm resistor is going to give a certain amount of power. A DC source voltage whose value is the root mean square voltage of this peak here, which means 220 volts divided by root 2. You will see that they give out the same power. That is our understanding of what the root mean square voltage or the root mean square current means. I illustrated from here on that the power component in a real resistor, when Z is a pure resistor, right? When Z equals to R, the power that is drawn from the source is purely real, right? So if Z equals to R, that means it's a pure resistor, then the power that is coming from the source is equally given by RMS times I RMS. And all the other equations, in their form, RMS squared over R or I RMS squared times R with I. However, when the impedance is not who is having a mic, please just
Test ezolo ngiyayibonga.
please mute.
Test ezolo wethu.
Thank you. Right. If that is not a pure resistor, that means Z is a complex impedance of the form plus or minus JX. That means it has got some resistance and some reactance. The reactance can be inductive, that would be positive, or can be capacitive, then that is negative. Then the power that is absorbed by the load is generally now defined as VRMS in phasor form times IRMS in phasor form by taking the complex conjugate of it, right? Now, this gives us, because the result of this maths here will be a complex number which has got a real part, which we call P, and an imaginary part, which can be positive or negative, which we call Q. Now, these three quantities, we gave them names, JQ. We called this here the reactive power, right? This is the reactive power. And it's measured in volt ampere. The reactive V stands for volt, A for ampere, and R for reactive. So altogether, it's VAR or VAR, VAR, volt ampere reactive. Of course, if it's small, it will be volt ampere reactive. It's a bit bigger, kilovolt ampere, megavolt, giga ampere, and all those other prefixes you can use. P is the real power that is absorbed by the load, and this is measured in watts. If your load is a motor industry driving a load, then this would actually be the mechanical output from the motor. That is the power that is actually exerted to drive the load. The reactive power is still reactive. We'll come back to that in a minute. And then S, which is a combination of these two, we called it apparent power. And this is measured in units of volt ampere. There is no R, so this is just volt ampere. And the three quantities, S, P, and Q, form a right-angled triangle relationship. That's not looking good. Let me try again. Right? So this angle here, you can determine it from there, right? If we call it theta, this side, which is the opposite, is, no, the opposite is this one, right? This is Q, this represents Q. Then the adjacent side represents P, and the hypotenuse represents S. So this is a right angle triangle, and all the trigonometrical relationships do apply, meaning that you can use Pythagoras. S squared is equals to P squared plus Q squared. Notice that I'm using magnitudes here now, right? So this S here is actually magnitude, P is magnitude. And theta is obviously given by the appropriate trig ratio. You can use sine, cosine, whatever you have. I've used the tan here, which means I can say it's arctan Q divided by P. Or I can say it's also arc cos. It's the same angle P over S. Right? That is the angle theta. And the ratio, right, of P over S, this ratio here, P divided by S, we called it the power factor, right? So this is also cos theta. That is called the power factor. And this is where I would like to pick the lecture for today in the remaining minutes. Before I do that, any questions?
Yes, sir. There are questions.
Yes, please go ahead.
Okay, sir. In that equation of apparent power, where S is equal to P plus minus JQ. Okay, are we going to use the same principle as the RLC when RXL rather is greater than XC? There will be a positive J there. Then when there is XC greater than XL, there will be a negative JQ there.
Okay, I will go back to this diagram, right? Remember when I was writing from the beginning, I said Z is equals to R plus or minus JX. And I said it is plus when it is inductive and it's minus when it's reactive. That I hope you understand or you remember from the lecture. And the same way when I came to write S, I still kept plus or minus JQ. Now your question, I hope I understand you clearly. The scenario which
Yes.
I've shown here in this diagram corresponds to an inductive situation where the reactive power Q is positive. Now, in the lecture, previous one, I did indicate that when the load is capacitive, then this triangle will be like this because Q will be negative, by which I implied if I were to show my full axis here, right? So this is my Y and then this is my X. This will be positive, that would be negative. So if we are talking of a lagging power factor is lagging when the current phasor is behind the voltage to give us positive Q. The power factor is leading when the current phasor is ahead of the voltage. It will give us a negative Q. So this here corresponds to a capacitor, cap for short, and this corresponds to an inductor. That is the situation. So yes, those plus and minus do apply in the context that I've explained. I hope that answers you.
Sure, sir.
Thank you. Any more?
This test was a flop.
No, let's keep to the lecture. Let's leave other things. Let's save time for this. Okay, I take it there is no further questions. I would like just to pick up from that point, but go back to these two equations which I have given you so that you have proper understanding. You see, at the beginning of today, I've shown you these two equations here, these two here, which I said are the general expression for current and voltage. The current has got its own phase leg or lead. I just showed it as alpha. And then the voltage, the same way, has got its own lead or leg as shown as phi. Now, if I were to draw a phasor diagram from these two sinusoids here, all right? So I would say V is equals to V peak angle phi. And then the current, I would show it as I peak angle alpha, like that. So this is your current phasor, and this is your voltage phasor. And the scenario again is just repeated here for emphasis. You have a load Z, which is going to be R plus J X. Sorry, I was going to write Q. X. Right? Like that. Okay. So there will be a current flowing, right? That current, we have already indicated it here. This is the phasor form of the current. and there is a voltage, which I've indicated here. Now, if I were to draw the phasor diagram for these two signals that I have, the voltage and current, I would probably have something like this. Now, remember, I did not specify the angles, neither did I specify the peak magnitude. So I'm just looking at a general case. That's what it means, right? So I may have my voltage doing this. I'll call that one my voltage, in which case the voltage phasor, which I'm showing phi, is this, right? I may have my current maybe like that, in which case the current that I'm showing the phasor is that, and that angle here is phi, right? Phi. So this will be these two complex of phasor equations or phasors represented in a phasor diagram. This is your real, this is your imaginary. Now, the point I want to emphasize is because of what I'm going to say next, right? Now, we are going to be talking about power factor. I'm shorting it here, power factor, PF. Now, when I'm talking about power factor, I'm talking about the angle between the voltage phasor and the current phasor, right? In this case, the voltage between the current phasor and the voltage phasor, as I have shown just in this diagram, will be this angle plus that. So the power factor angle in this case here would actually be phi plus this. That would be the power factor angle. That is the angle difference between the voltage and the current phasor. If I had another scenario like this, right? So now I've got my voltage phasor is like that. I'm going to use the same labels. This is the angle. And maybe this time the current phasor is like that, meaning that the current phasor is all the way here. Hello, Siskon. I'm good. I'm having a class, my friend. Online class. Yeah, it finishes around, but I'm going to finish at 12, at 10 two angles. In this case, the effective power factor angle will actually be alpha minus phi. You see, because it is this angle here. That will be the effective power factor angle, theta. That is the angle between the voltage phasor and the current phasor, right? So I hope you understand it from that context. So when I shall say the power factor angle, I will mean this or that, right? In its proper context. So in general, we normally use this form here, where we take the voltage phasor as being 0 angle, and then our current phasor is either here or up here. So this angle will say it's theta. So power factor is then equals to, power factor angle is then equals to theta, because this voltage phasor is simply at V peak angle 0. You see, so this is the normal situation I'm going to talk about. Now, this is equivalent to saying that if you go back to your circuit here, your voltage is simply V peak sine omega t. The phase angle is 0, so VI equals to that. That's your source. The phase angle is 0. And then this here, the impedance, if you express it in polar form, magnitude of Z, and then the angle becomes theta, right? You know how to get that angle. It will be arc tan X divided by R. So when you have this scenario now, this power factor angle actually is equals to tan minus 1 X divided by R, right? Where Z is equals to R plus or minus JX, right? So that in general is what we are going to be calling the power factor angle. And the ratio, the cosine ratio of it is what we call the power factor. Power factor is leading in an inductor and power factor, it's leading in a capacitor. Let's correct that. It's leading in a capacitor, and then it lags in an inductor. Lags leading, it means the current is behind the voltage phasor. This is inductive. Leading means the current is ahead of the voltage phasor. So this will be a leading current. This will be a lagging current, right? The voltage being at 0 phase. Now, having said this now, we want to now understand where does this concept of power factor take us to? And why talk about it at all? I'll check my time, how much I have. Okay, about 4 minutes. I won't continue very much at this point, but maybe ask any questions on the little things that we've covered so far. Because it's only 4 minutes. I would rather leave it at this point. Are there any questions? Please.
No, sir.
Okay, let me see here. Denzel, are you with me?
Yes,
Denzel, what is power factor?
Power factor, sir, I can define it as a. I think power factor, sir, is the angle between voltage and current.
Not quite. That is the power factor angle. The power factor is the cosine ratio of that angle. Yeah, so you're on the right path, but just to make it more correct.
Okay, sir.
Bali, what do you understand by real power? Bali, Valencia.
Yes, sir. Sorry, I got distracted. I'm sorry.
Yeah, what do you understand by real power?
Is it not the power consumed due to the resistive load?
Well, it can be resistive load, but I did indicate that if you have a motor is not a resistor, you see.
True.
But a motor is used to drive mechanical load. The load can be a grinding mill. If you are in the process industry, it can be a hooper, it can be a conveyor belt in a mine carrying stones and all that. That unit is doing work because it's exerting force, causing motion. So there is power there, but it's not a resistor. So
real power is the power that is actually used.
is the real power
Like the
that
true
is
power.
used, yes, to do mechanical work.
All right.
Okay, Bonginkos, what is reactive power then?
A reactive power is the resistive power due to the reactive components.
I know you understand it, but it's a concept which at the beginning is not easy to define. And to do justice, I have not yet defined it to you, but we have explained it mathematically. So yes, for now, I would say, a sufficient answer on your side would have been to say the power that is absorbed by a capacitor or an inductor. But there is no resistance there, right? So remember, the minute you start talking about reactive power, the resistor is out of the picture. It is about inductance, it is about capacitance.
So can I ask?
Yes.
The reactive power, can I define it to be the power lost?
No, you cannot. Just keep your question as we carry on. Just remind me again to answer the same question. But it is not. You see, I will give you an illustration in the following lectures. Just keep that question, and then ask me if you see that maybe I've forgotten to come back to that issue. For now, it is 10 o'clock. As I have said, I'll request extra time to cover this material. The objective is for this section of the course is we want to be able to understand why power factor is important and what is the desirable power factor. What are the consequences of having a poor power factor and how do we correct it? If we can understand that, then we would have achieved the objective of this part of the course, and then we will leave that part and move on to circuit analysis techniques. So thank you very much for your attendance. God bless you. We'll meet again in the next lecture. Bye.